Hello everyone, I am Ayush and I work as a software engineer in the integration squad at Postman. Today, I will be talking about using Async API schema to define event-driven architecture with AWS SNS. As this talk is intended for beginners, we'll first start with defining very basics like what is an event, what actually is an event-driven architecture. Then we'll talk about what is AWS SNS and why is it useful. After that, I'll talk about what was the use case we had at Postman and how Async API helped us in solving that problem quickly and efficiently. So let's start with defining what is an event. So an event is any significant occurrence or change in the state of a system hardware or software. I'm adding hardware here because the changes might include from a separate IoT device to change of a sensor value or things like that. You might have heard about event notification in different contexts before. It is actually quite different from event because event notification is a message or notification sent by the system to notify another part of the system that actually an event has taken place. So it just acts as a message or a notification service for an event, as the name suggests. An event can actually carry in-depth context information of what has actually happened, or it can just have an identifier, in which case you have to call the necessary APIs to get more contextual data regarding the event. Let's come to what actually is an event-driven architecture. So it is an architecture which uses events to trigger and communicate between decoupled services, and it is actually quite common in modern applications built with microservices. So an event-driven architecture has three basic components. First is the event producer. It is the part where the event actually originates. Then we have an event consumer. The consumer is the part of the system that has to perform certain actions on the occurrence of the event and needs to be notified of new events. Now, the third is event router. So it is a connecting link between the event producer and the event consumer. In certain cases, it can actually also act as a filter and block certain events to be delivered to some specific consumers so as to not overload them with various unnecessary events. In this architecture pattern, the producer and consumer are completely separated from each other and communicates only through the event router. For example, we can take a simple system of Bitcoin price change notifier, which should send an email notification if the price is above a certain limit only. So in this simple system, we can have a simple cron job which fetches the current Bitcoin price using the necessary APIs, say every few minutes, and it has to send it to the router then. So it will be our event producer. Now we will have another service which sends out email notifications. So this secondary service will have only single job to send the email notifications wherever it is we have configured to. Now this actually will be our event consumer. Now we will define our router to publish price change event to email notifier only if the price is above the limit. And we might have a separate use case in which there's a third service which needs to be notified on every price change. So that could be our secondary consumer, and this is the reason why a filtering mechanism might be required on the router level. Now let's talk about like what are the different benefits of using an event-driven architecture. First and foremost is like parallel processing. So say on occurrence of an event, you wish to perform a large number of heavy actions. With event-driven architecture, you can execute them in parallel without any hassle. One can actually add separate consumers for the actions to be performed, and each will get triggered individually on receiving the event. This will actually also ensure failure of one action will not affect the another, which might occur if you're using a traditional synchronous system. Second is a versatility in choosing the technical stack. So, since producers and consumers are completely decoupled in event-driven architecture, it allows the user to use different software stacks for both, and same hold true for individual consumers too. One can have a producer which is say using Python to generate the events, and consumer might can be written in Node.js for some optimization purposes. This is actually pretty useful in efficient working of complex systems too, like in which in which like say one part could be written in a high level language for better abstractions and support of better libraries, and another the consumer side could be written in a low level language for better performance and optimizations. Now, the third we have is like hassle free cross team dependency. So, to explain it, let's take an example. Say in a company, there are three teams A, B, and C. They are already using event driven architecture to communicate, in which A publishes an event and B and C consumes them and performs some actions. Now, say if a new team comes, new use case comes for team D, in which it actually needs to perform some actions on the events which A is producing. Since they are already using the event driven architecture, there will be no work required to be performed by team A. Team D just needs to subscribe to the events on the event router and it can start processing the events effortlessly. Apart from this, event-driven architecture also allows producers and consumers to scale independently. So, if say the producer is getting a lot of traffic and a consumer is just triggered on very few subset of events, we can have much better scaling for producer, and we can have less number of instances for consumer. Now, let's talk about what is actually SNS. So SNS stands for Simple Notification Service. It is an AWS service which acts as a event router to provide message delivery from producer to consumer. It actually has a inbuilt filtering mechanism which allows consumers to get triggered only on the matching subset of events and not on all the events which are published, uh, which saves the compute costs for consumer a lot. The communication between producer and consumer happens via topic, which is the logical access point and communication channel for SNS. So consumer subscribes to a SNS topic, and whenever the producer sends an event to the same SNS topic, consumer receives it and performs execution. Because of this, SNS all topic also groups the set of producers and consumers together for easier maintenance. Let's see like how this actually works. So in this case, here is the producer, which will send event to SNS, and SNS can then forward this event to various different services. Like if the whole infrastructure is in AWS, it can easily send the events to Lambda, Kinesis data, SQS, HTTPS APIs, which you have. Apart from this, it can also actually send push notifications, email notifications, and say SMSs directly through SNS without using any other external service. Now, uh, I mentioned like the SNS actually allows you to filter messages. Let's take a look like how does that message filtering works on SNS. So when a producer publishes a message to SNS, along with the payload, it can actually attach some key value pairs to the message, which will be used in filtering. So point to note here is that you cannot directly use the payload data for filtering purpose because SNS also allows you to encrypt that payload data for better security. So when the consumer creates a subscription with SNS topic, it can actually provide a optional filter policy to receive the subset of events. The filter policy will work on the attributes which the producer is sending along with the message payload. So the as you can see, the producer is adding some attributes. Consumer, while adding the subscription, tells like which for the value of which attribute should be triggered for this particular event to be sent to the consumer. So this filtering logic is completely Boolean. Either it matches the filter policy or it won't. So when it matches, it delivers the event, and if it is not, it just skips the consumer and checks on the next one. So for a particular message to match, so if in the filter policy you have added say three different attributes, all of them should return true for it. It's not like if you added three different subscription filter policy, three attributes there, and only one or two are matching and third one is not, it will not deliver the message to that particular consumer. The third point here is the attributes of the message not mentioned in the filter policy are ignored. So if say your producer is sending five different attributes and for the filter policy we have only three, the other two attributes will be completely ignored without any hassle. Also, the one thing to remember is the matching is exact without any case folding or any other string normalization. So you have to keep that in mind while adding the filter policy. Also, the number matching is done on the string representation itself. So 300 is not equal to 300.0. So this is a very important gotcha for this if you are working with SNS. Also, the value of each key in the filter policy, which we are defining on the consumer subscription level, is an array containing one or more values. So the policy matches if any of the values in the array matches the value in the corresponding message attribute. So if in the filter policy for a attribute A, you are setting the value of the arrays as 1, 2, and 3, and the message attribute has the value as 2, it will get matched. So, but if the value in the message attributes in itself is an array, then filter policy actually matches it if the intersection of the policy and the message attribute array is non-empty. This is how the subscription works. Let's look at a diagram to see like how this actually happens. So here, ignore this ingester for now. Say we have two producers, monitor and collection. They are two separate producers. Monitor sends event A and B. Collection sent event C. uh, all these events, these are the message attributes attached. The attribute key is event type and event action. Um all those three different values are added. We have two separate consumers. SQS one is our first consumer here. SQS2 is the second one. For SQS1, we have defined the filter policy as this, like event type can be monitor or collection, and action can be monitor run finished or collection updated. Similarly, in SQS2, the second consumer, we have type defined as monitor and collection, and action could be monitor updated and monitor collection updated. So when these three events reach at SNS, let's see individually what happens. So let's say first the event A approached SNS. So it will first match the filter policy, try to match the filter policy of first consumer. Event type, as you can see, it's monitor. Monitor is present in this array. It matched. Event action is monitor unfinished. Event action here is also monitor unfinished. It matched. So it will send the event A to SQS1. Now it will check for SQS2. Here, though event type matches, but event action is not present in this array. Hence, it will not send this event here. In case of event B, the type and action, which is monitor updated, the action is monitor updated here, matches for the policy of SQS1. So it will send the event B here for the first consumer. When it checks for the second consumer, again it matches. So it will send a copy of event B to SQS2 also. So producer sent the single event and it gets fanned out on the consumer level at SNS. Similarly, in case of C, the filter policy at SQS1 doesn't match, but at SQS2 matches. So it sends the event C only to SQS2. So this is how the message filtering at SNS actually works. Now, I would like to talk about what was the use case at the integration squad in Postman. So we wanted to allow different teams to easily send relevant events occurring in their domain to us. Then we would then process those events and trigger relevant integrations. So as the producers can be large in number in our case, like different teams at Postman, we wanted the service to be completely decoupled, requiring minimal changes on their side for faster adoption and less maintenance for future. In future, we might actually need to add more producers to the service also. Hence, we wanted it to be easy and fast for the new teams to start publishing their events. So it should not be like they have to do a lot of development work to only enable the publishing of events also. Lastly, there could be other teams also which might want to perform some actions on the some of the events we are receiving. So to prevent them from reinventing the wheel, we wanted it to be easier for them to start consuming the events which we are using right now. So now I'll like to tell like different approach we used for the solution, and then I will talk about like what was the final approach we decided to go with. So this was the approach one. So here, ingester is just a small service which performs some validation checks and adds an abstraction layer to communicate with SNS. So all the different teams just send their events to ingester. Ingester validates and checks the event payload, adds corresponding message attributes, and then publishes them to SNS. Then SNS, at SNS we have like different queues for each team. At the end of the queue, we had a router, and the router actually sits at the end of SQS, and it essentially works as a switch. So consumers will be connected to the router. Router will be connected to the queue, and whenever an event comes at the router, it will check like whether which consumer wants to listen to this particular type of event, and then it will just fan out to those consumers at that level. So the technical stack I thought initially would could be a lambda sorts for the router. So there were a lot of issues in this whole design. First of all, there were problems with router, like constant update needs to be added on the router for any new consumer added or removing an existing consumer. Router needs to be updated. There would be added costs and maintenance overhead for the routers too. So that was a problem. Another thing is consumer has to know which particular queue and router it has to subscribe to. And adding a completely new domain, like let's say we have like four domains right now: collection, monitor, API update, team, activity. Adding a new domain would require a lot of infrastructure changes. Like we have to add a new queue router connected to the SNS, which is very much hassle. So at the end, we finalized on this. So event producers will publish events to ingester. Ingester publishes those events to SNS, and after that, the whole infrastructure would be owned by the consumer. So if say consumer wants to add a queue, they can add an SQS queue, and then their consumption logic, they can add a direct HTTP API to SNS, and the filtering part would be completely owned by SNS itself. So provide more autonomy to the consumers as they can define how they want to ingest the events. Um, and as I mentioned, the filtering was done at since the filtering is done at SNS level, it removed all the maintenance overheads we had. So this is the workflow we finalized on to for our use case. Now, I would like to discuss like how Async API helped us. So one of the first and very foremost thing which Async API added in this whole process was easy review of payload and the event structure. So there was a separate team which will be generating the event. Then our team would be consuming those events. So the coordination needs to be precise here. So Async API helped in that. It actually allowed the producer and the consumer here, in our case, to start working parallelly without any dependency on each other. Then the API schema actually provides a one-stop repository for future teams also to so that they can check the event payload whenever they want to create a or add a new subscription, allowing faster adoption of this particular schema. So wh- this is just a depiction like how what would happen, like could have happened if the async API schema was not present for us. The producer side might have been working on their side of changes. We might be working on our side of changes, and when it's finally time to merge both, uh, something like this could have happened. So async API actually helps us to avoid this kind of a situation. Now, I would like to define some essential components of the async API schema which we use. Uh, First is servers. So, uh, before servers, actually, there's a info block also, which is mandatory for the schema. It contains the basic information like the title, description, and the version of the API schema which you are using. Servers actually allow you to define like a different entry consumption or the entry points for the events. It will be using for communication. So this here production is just a reference or identifier for the server. Then we have the URL, like what will be the URL of the server. Protocol, we had like HTTPS, but you can use any supported protocol here, like HTTP, AMQP, MQTT, WebSockets, anything which you like. Description is just to define like what this server is, like whether it will be running in production, whether it is just for testing on stage, this kind of a thing. Then we have like security, like what kind of authentication it will be using. The basic auth here is just an identifier, which I used in my schema. How the security is defined will be coming on to next now. Security, so as you can see, this components inside the components, we have security schemes, and here we define like what type of authentication we want. So basic auth, as I mentioned, is an identifier. It can be anything ABC, which would be used in the previous slide if we used. type user password. So for me, the authentication scheme is user password authentication, but you can use various other supported authentication schemes like OAuth 2, API key, just to name a few. Like there are a lot of supported auth schemes which you can check out on the documentation page. And description is just self-explanatory to define like how maybe you can get the auth credentials, where to look for the auth credentials, or how it has happened, why it has happened, things like that. After that, we have channel and schemas. So first, let's talk about channel object. It actually holds the relative path to the individual channel and their operation. The path here would be relative to the server. It is actually known as topics, routing keys, event types, or paths also. This is the basic schema for the channel object. It looks like this. Like for the, it could be here the subscribe could be, let's say if it's a producer, it could be publish. Then message schema is defined in the separate component so that it's more modular. Then we have a schema object. So schema object allows the it actually allows you to define the input and output of the data types. It can be the object can it can be an object, it can be a primitive array, things like that. It can actually be directly used in the reference object like we are doing here in the channel object also. We are just add the path to the object and it will be directly used whenever you're, let's say if generating the HTML or a markdown of a particular thing. So that's it from my side. Uh, this was the end of the talk. Thanks a lot for listening. These are my handles on different platforms if you want to connect. Uh, Thank you. Thanks a lot.